In this video, let's talk about elasticity of demand and income. This is definitely business calculus, economics, finance example. You may have seen it before in those courses, but if you have not, I definitely recommend to read the text. Wiener Constantinople is the text that we're using. And page 433 to 437, that whole section, they actually explain it very well. But basically the idea is you can track how elastic the demand is, which is basically how responsive it is to changes in price. We know from basic economics that the demand would increase as the demand would decrease as price increases, or vice versa. But we can also track how drastic the change in demand versus increase in prices. For example, it could be elastic or basically react strongly to a change in price, or maybe the demand could fall drastically. It's to me, I think it was a little bit surprising, but the luxury items, well, maybe they're not must-have items. That could depend on economy. But for example, automobiles, home loans, jewelry, etc., if the price changes too much and to become higher in the increasing version, then the demand may drop drastically, especially if it's not a must-have item. But on the other hand, essentials like water, gas, etc., may be inelastic, so the price could increase, but the demand may not be as sensitive. Basically, how we're going to track it mathematically, it's what's the percent increase or change versus of demand versus of price, for example. So we're going to denote delta as change or difference in quantity. So if we have Q as quantity, that's how we can track the demand. How many items are sold versus what the price is. So this is how we can derive this quantity, which is called elasticity. I shouldn't call it quantity, maybe this function, maybe this number, but we're gonna call elasticity E, and this is how we're going to define it and track it. Is what's the difference in demand, which is delta Q, change in Q, versus divided by the actual amount Q, versus, so this is how you track percent increase or decrease. I'm gonna put minus for the demand, and the price, let's say the price increases, so it's positive. How much does the demand decrease? So this is how you track the percent increase or decrease. Divide the difference by the original amount. Now, you know how we can flip fractions, so we can write it as negative delta Q over Q times, so let's flip the bottom fraction, and we'll get P over delta P. Now, note that you can put the deltas together in this fashion, and times so negative delta Q over delta P times P over Q, or you can replace it with the derivative. If the changes are small, we can actually track it as the derivative. So we're going to obtain negative dQ over dP, or the derivative of demand Q in terms of price P, times P over Q. So Q usually would be demand in terms of P. P would stay as a variable. Q would be the equation in terms of P. Now, something to keep in mind, that the demand is inelastic if elasticity is less than 1, which means it's not very sensitive. Maybe the demand only drops by 0.5% when the price increases by 1%. So it's not very reactive to the price change. Versus the demand is elastic if E is greater than 1, which basically means the demand drops maybe by 2 or 3% when the price increases by 1%. So it reacts strongly. And the unit elasticity, which we will see is actually ideal situation, the price is just right, the Goldilocks principle, E is equal to 1. We're going to see the graph of revenue. So we know how revenue is price times quantity, and we can relate elasticity to revenue. So it turns out that if we measure price versus revenue, so when elasticity is 1, the revenue is actually at a maximum. That's an alternative way to compute maximum revenue. Instead of finding the derivative and setting it equal to 0, you can actually find elasticity and set it equal to 1 and solve for price. So when the price is just right, we have maximum revenue. If the elasticity is inelastic, if it's less than 1, then the revenue actually is still increasing as price increases. That means the price may be too low, and it could afford to increase a little bit higher. On the other hand, when the demand is elastic, that means the price is too high. So this is how we can relate it in terms of price. So let's see a few examples in this section. Let's say, and this is from page 431, and the first example, first problem. Let's say we have demand for oranges. Keep in mind this is in Hawaii, so the price for oranges may be outrageous. Yes, $30 per orange. Maybe it's not that high, but it could be pretty pricey in Hawaii. Anyway, the weekly sales of Honolulu red oranges is given by, notice here's our demand equation, Q equals to 1000 minus 20p. So notice how Q is equated in terms of P. Calculate the price elasticity of demand when the price is $30 per orange. Yes, $30 per orange. Okay, so let's see how that works. First, we need to calculate elasticity, and we derived this earlier, but from now on we're going to use this. So it's derivative of demand, dq over dp. Remember, it's like the rate from related rates section times p over q. So what's the derivative of the demand? If you remember, it's 1000 minus 20p, so the derivative of it, 1000 is a constant, it's gone, but we get negative 20. So we have negative on the front for the decrease of demand. Negative 20 is the dq over dp, the derivative of demand, times p on the top, that stays as a variable, divided by the demand equation, which is q, 1000 minus 20p. So if you notice, negative and a negative usually cancel each other out. So we're going to obtain 20 times on the numerator times p, so 20p in the numerator divided by 1000 minus 20p. You don't really have to reduce it. I guess you could have reduced it, but let's leave it for now. So what happens if we plug in a certain price? We can calculate the elasticity. So if I plug in 30, so 20 times 30, so you'll get, I think, 600 divided by 1000 minus 20 times 30. So I think it's 600 divided by 1000 minus 600, 400. So we're getting 1.5. So first of all, the demand is elastic. It's bigger than 1. Definitely the price is too high per orange. But what's happening is the demand is going down by 1.5% per 1% increase in price. This is how you can interpret it. I think on the homework, the setup would be very similar. And the revenue is maximum when E equals to 1. You can also calculate which price would give you maximum revenue. So you take that same elasticity we got above, set it equal to 1. Note you can multiply both sides by denominator. And because it's just 1, we're going to get 20p, so it cancels on the left. And then on the right, it would be 1 times 1000 minus 20p, which is basically itself. And we can add 20p to both sides. And so we'll get 40p equals to 1000 divided by 40. And we get $25. So $25, I suppose, I guess, is reasonable for Honolulu, Hawaii. And that would be the price that gives maximum revenue. How can you find the actual revenue? Do it price times quantity. So price is 25. Remember, Q was we can use the demand, 1000 minus 20p. So 1000 minus 20 times 25. And so we actually get $12,500. So basically plug it back in. And in general, this is how we do all the problems, as long as we understand the setup of elasticity. Let's take a look at number 3. The consumer of demand equation for tissues is given by Q equals to 100 minus P quantity squared, where P is the price for case of tissues and Q is the demand in weekly sales. So demand or quantity, they're both interchangeable. So first of all, we need to calculate elasticity, and when the price is set at $30 per case, again, like previous example, and interpret your answer. So first thing would be to find the derivative of the demand with respect to price, dq over dp, which you may have recognized. You need to use chain rule. So we bring the 2 down, 100 minus p stays to the 1 power, times derivative of the inside, which is -1. And we can multiply -1 by 2, so we're getting -2 times 100 minus p. So that's the derivative. This is what we plug in for. It's sort of like the rate of change, except in related rates, we had to do it with time, and here it's like the direct derivative. So let's plug it in into elasticity. So negative, and then inside is the derivative, negative 2 times 100 minus p. I actually did not distribute, and you will see why in just a second. And then times p over the original demand equation, which was 100 minus p squared from before. Now note, negative and the negative will cancel each other, so you'll actually get positive 2 times 100 minus p times p. Again, I did not distribute because you note you can actually cancel it with the bottom. So what do we get? We get 2p on the top and 100 minus p, now it's not squared anymore, on the bottom. So occasionally you can simplify it quite a bit. So when p equals 2, I think I meant to put 30, not 20. I think this is a typo, because did I get this right? Yes, I think it's 30, because if you plug in 30, 2 times 30 is 60, and then 100 minus 30 is 70. So this is a typo. Let me actually fix this real quick. So yes, make sure to fix this in your notes. So you get 60 over 70, or as a decimal, 0.857, or 6 over 7, however you want to do it. But this time, elasticity is less than 1, so the price per case of tissues may be too low. Maybe it needs to be higher than $30. But how do we interpret it? The demand is going down, or decreasing, by 0.857% per 1% increase in price. Okay, so very simple the way to interpret the results. So very simple so far. Now, at what price should tissues be sold in order to maximize revenue? Again, we set the equation for elasticity equal to 1. It was 2p over 100 minus b equals to 1. Again, multiply both sides by denominator. So we get 2p equals to 100 minus p. Add p to both sides. We get 3p equals to 100. Divide by 3. And so I'm getting $33.33. So it needs to be a little bit higher than 30. Maybe this is not an ideal round price, so you can, I guess, experiment in the actual business situation. Now, approximately how many cases should be demanded at that price? Note, that's really actually we're being asked for quantity or demand. And you can plug in P 33.33 inside of the demand, and it's approximately to the nearest whole number, because we're talking about cases. It's 4,444 cases, and so quite a few cases. All right, here is the situation with colleges and universities charging tuition, which is quite applicable. So let's take a look. A study of about 1,800 U.S. colleges and universities resulted in the demand equation Q equals to 9,900 minus 2.2p, where Q is the enrollment at a college or university and P is the average annual tuition plus fees that it charges. So, also the study found that the average tuition charged by universities and colleges was 2,900. That was probably years ago, or maybe decades. But what was the corresponding price elasticity of demand? Is the price elastic or inelastic? So here we're actually asking to interpret elasticity. And how should colleges charge more or less on average to maximize revenue? So very applicable again. Note, maybe pause for a second, try to figure out how did we get this elasticity. Remember, it's negative, start with a negative, and then the derivative of the demand, which is actually also negative 2.2. It's just a constant. So negative of a negative becomes positive, which is how I got 2.2. And then remember, it's times P divided by the demand. So this is how come I got this equation. Again, do not worry about simplifying it. When P is 2,900, plug it in. Make sure put the bottom, the denominator in parentheses when you're putting in a calculator. And I get elasticity as 1.81, which is greater than 1. So what does it mean? Well, it's bigger than 1, so the demand is elastic. So the decrease in tuition will result in increase of revenue. Basically, in our own words, yes, the university should decrease price, or charge less for tuition. That actually is not that surprising in order to maximize revenue. Now, based on the study, what should you advise a college to charge in order to maximize the total revenue, and what would the revenue be? Again, pause maybe the video for a second. Can you answer this question? And we can set the equation equal to 1. Again, multiply both sides by denominator. Add 2.2p to both sides to bring it over to the left-hand side. We get 4.4p equals 9,900 divided by 4.4. It's roughly $2,250 per student. And the revenue is big in that college. Well, relatively, I guess. Again, speaking for maybe earlier time. If you plug in as P times Q, plug in 2250 for P, and we get about $11,137,500, which is pretty significant for college or university. Now, the last couple of problems in that section are income elasticity of demand, which is similar, but because income is directly let me read the definition first, and then I'll try to talk about it. So income elasticity of demand is percent increase. So this time it's direct relationship instead of inverse like with the demand, but it's percent increase in demand for a particular item divided by percent increase in personal income. So we're talking about luxury items, so that as income increases, then the demand for a particular item, maybe if it's a luxury item, or maybe it's going to a live performances, which we'll talk about, or concerts, so the demand for that would increase as well. So we're not going to see a negative like we did before with the demand. So notice if we define x as income, then we have dq over dx. So once again, we have q, it's for the demand. This time it depends on x, which is income, times x over q. So basically, yes, let's talk about this. Here's number 17. The likelihood that a child will attend a live theatrical performance can be modeled by, and it looks a bit complicated, but it's 0.01, and then it has like this quadratic with decimals equation inside. So here, Q is the fraction of children with annual household X $1,000. So notice X stands for, depending on the units, the income, who will attend a live dramatic performance at a theater during the year. Compute the elasticity of demand at an income level of 20,000 and interpret the result. Got to be a little bit careful with units. If it's 20,000 and we're talking about thousands of dollars, you may have to divide by 1,000, and x could be 20 that you're plugging in. So you're not actually plugging in 20,000. Round your answer to 2 significant digits. So x is 20,000. This is what I mentioned earlier. So we compute elasticity similarly. Again, there is no negative because the demand would increase. So and then let's take the derivative. So remember, 0.01 is just a constant. So I actually kept it. And you'll notice it will cancel out with the denominator. Then let's take the derivative. Negative 0.0078 times 2 is actually negative 0.00156 x. And then plus 1.5x becomes 1.5, and 4.1 is a constant, so that's gone. So that's the derivative. Times x divided by the original demand function. So notice you can cancel out 0.01 to make it a little bit cleaner. So you just get the derivative times that x, already distributed, divided by the remaining expression in denominator. Now, try plugging in 20. Again, use your calculator. I would put parentheses around the top and the bottom this time. So when x is 20, I'm getting 0.77. So what does that mean? At a household level income of $20,000, the percentage of children attending a live theatrical performance is increasing by 0.7% per 1% increase in household income. It sounds like a mouthful, but it should make sense. So the percentage is increasing by this much per 1% increase in income this time instead of price. And that's it for this section.